So we've talked about the Bohr model of the hydrogen atom and how electrons can only be found at certain distances from the nucleus. But Bohr also did some mathematical calculations as well, where he was actually able to predict the energy of an electron in a hydrogen atom, depending upon which Bohr orbit it's in. And that mathematical relationship that he developed was given in the introduction to experiment 3. And that particular equation is this: E equals negative K divided by n squared, where the E in this equation stands for the energy of the electron in a hydrogen atom. K is just a constant. We now name that the Bohr constant. Has a numerical value of 2.178 times 10 to the minus 18th joules. If we want to measure the energy in the units of joules, you can measure energy in different units. There's ergs and foot-pounds and electron volts, but we would like to do that in the metric system, and the unit for energy should be joules. So when you're doing calculations with this equation today, I would like you to use that particular constant. And then the n in the denominator stands for what Bohr orbit the electron is in. So this is going to allow you to determine what the energy of an electron is in a hydrogen atom. Now, the energy you're calculating is a potential energy. And there's actually two types of potential energies. There's a potential energy for attraction, and there's a potential energy for repulsion. So in physics, they wanted a mathematical way to differentiate between attraction and repulsion. And so they've decided to do that with the sign convention. So whenever you're talking about an energy value, the sign is important. If you have a positive energy value, that means that's a repulsive energy between that material or that object and something else. If you think about when things aren't very good for you, if you're standing at the very top of the Empire State Building looking over, whoa, you do not feel very good, and you're really high in the building, you have a high amount of anxiety and energy, that's bad. So positive energies have been associated with repulsion. However, if you go down the elevator in the Empire State Building and you get down to the ground floor and you stand on the sidewalk and go, oh my gosh, I feel so much better. You release all the anxiety. You have a low amount of energy then. And what's a low number? A negative number. So we define negative values for energy as attractive energies. So if you look at the equation that Bohr used to calculate the energy of an electron in a hydrogen atom, you notice there's a negative sign in it. That means that the energy of the electron that you calculate with this equation will always come out negative. Why would that be? Because the electron is in one of the Bohr orbits and it's next to a positive nucleus. So the electron will always be undergoing attraction when it's in an atom. So that means its potential energy that you calculate should always be a negative number. So therefore, any calculation you do for the energy of an electron in a hydrogen atom will always come out to be a negative number, because by definition, we want negative values to mean attraction, okay? So that's the equation given in the introduction. Let's try an example where we actually use that. Let's see if we can calculate the energy of an electron that's in the third Bohr orbit of a hydrogen atom. So this calculation can just be done with this equation. We use the Bohr constant, 2.178 times 10 to the minus 18th joules, and then you just put whatever the Bohr orbit is in the denominator, and in this case, the electron is in the third Bohr orbit, so we put 3 in the denominator, and then you square it. Now, the constant in the numerator here is a 4-digit number. Now, is that a defined number? Is that an exact number? Well, it's not defined. Nobody defines constants. Nobody defined the speed of light. Nobody defined Avogadro's number, and nobody defined the Bohr constant. Nobody defined Planck's constant. These constants are measured quantities. So therefore, that's a 4 significant figure number, and you have to take that into account when you're going to determine the significant figures in your answer here. Now, the number in the denominator is the Bohr orbit you're in. That's a counted number, so that's not a measurement, so you do not use the denominator for significant figure determinations. So when you do the division here, you should wind up getting a 4 significant figure answer. Now, on your calculator, and I think we've actually corrected a few people that were doing this wrong already, but let's just point it out. If you want to enter that number in the numerator, the negative 2.178 times 10 to the minus 18th, the way you do it in your calculator is you plug in 2.178 and you press the change sign button so it becomes negative. But now what you do not do is you don't press multiply, then you don't press 1 and 0, and then you don't do a caret, and then you don't do negative 18. You have a button on the calculator that means times 10 to the, and that button is usually either EXP, or in this calculator, it's the EE. So that's the second function. You press this button, and then you're pressing EE, which means times 10 to the. And when you do that, it's going to put a couple zeros on the very right side of your calculator screen. And now you put in 18 and change sign, or you could put negative 18. And once you've done that, the calculator will look like this. And what it's actually saying is negative 2.178 times 10 to the negative 18th. It's really not saying negative 2.178 to the negative 18th power. So sometimes people read it that way, and that's just because they're used to looking at their calculator, but that does not mean that at all. It's negative 2.178 times 10 to the negative 18th. Once you've entered that, then you divide by 3 squared, and you'll get your answer. And the answer should come out 4 significant figures. When you do this calculation, your calculator will only show negative 2.42 times 10 to the minus 19th, because it turned out randomly to be an exact number. But if you have to give the answer to 4 significant figures, don't write negative 2.42 times 10 to the minus 19th. I'll be waiting to mark that wrong on the lab if you do that today. You've got to put that 4th significant figure, so negative 2.420 times 10 to the minus 19th. It's a negative value. That means the electron is undergoing attraction when it's in the 3rd Bohr orbit of a hydrogen atom. So that's how you use the Bohr equation. Now let's talk about the type of calculations you're going to be doing in the lab today. You're going to be calculating the energy changes when an electron drops from one Bohr orbit to another. So I'm going to do one example calculation of that. So we're going to calculate the energy change when an electron drops from the 2nd Bohr orbit, which would be designated n equals 2. You could call that the 2nd energy level as well, down to n equals 1 in a hydrogen atom. So in a calculation like this, it's really, you just have to do 2 calculations. You have to calculate the energy of the electron in the 2nd Bohr orbit. You have to calculate the energy of the electron in the 1st Bohr orbit, and then you subtract those. That'll be the energy change. So let's go through those. The energy of the electron in the 2nd Bohr orbit. Now I'm doing a couple of calculations in the same problem, so I'm going to identify my E value a little bit more explicitly by writing E sub 2. So that means the energy in the 2nd Bohr orbit. So that's going to be negative K, negative 2.178 times 10 to the minus 18th joules, divided by 2 squared. The numerator is a 4 significant figure measurement. The denominator is a counted number, so don't worry about that. So the answer is going to come out 4 significant figures. So if your calculator doesn't show you 4 significant figures, that means you need to add a 0. But if it does show you a bunch of significant figures, round it to 4. And so this one should come out negative 5.445 times 10 to the minus 19th joules. We'll do the same thing, calculate the energy of the electron in the 1st Bohr orbit. I'll call that E sub 1 to represent the 1st Bohr orbit. So this will be our negative K value again, divided by the Bohr orbit squared, and you can probably even do this one without your calculator, I'd imagine. So that's going to come out 4 significant figures, and I get negative 2.178 times 10 to the minus 18th joules. Okay, so now we have the energy of the electron where it's starting in the 2nd Bohr orbit and where it's ending up in the 1st Bohr orbit. So when the electron transitions from one to the other, it's going to either release or absorb the difference of these 2 energies. So what you're really calculating is an energy change. And when you talk about changes in energy, usually that's written as a delta sign, which looks like a triangle. It's a Greek letter delta in front of the E. That stands for change in energy. So the change in energy, symbolized by delta E, is going to equal the final energy state minus the initial energy state. So what's the final energy state? That's where the electron is winding up at the very end. That's the 1st Bohr orbit. So you're going to go the final energy state, E1, minus the initial energy state, where was it starting, in the 2nd Bohr orbit, E2. So the proper way to calculate the change in energy, and this would be true for changes in temperature or changes in velocity, any change at all, we always go final state minus initial state. And so now we plug the 2 numbers in. The initial energy, actually the energy in the E1 value, the final energy state, was negative 2.178 times 10 to the minus 18 joules. And you subtract a negative 5.445 times 10 to the minus 19 joules, and just realize you've got a double negative there. So really that becomes an addition problem. It's the negative 2.178 times 10 to the minus 18 joules plus 5.445 times 10 to the minus 19 joules. And when you do that operation, I wind up getting a negative value, negative 1.634 times 10 to the minus 18th joules. Now, why are we going final minus initial? If you did it the other way around, and if you went E2 minus E1, you know what answer you'd get? The same thing, 1.634 times 10 to the minus 18th joules, but it would be a positive number. The reason we do it this way is that physics wants to have a definition for when you're calculating changes in energy. Because when you change energy, you can either be absorbing or releasing. So for changes in energy, if you get a positive number, that is going to mean in physics energy was absorbed. If you get a negative number, that means energy was released. So the only way you can make those definitions hold is if you always subtract the final state and then you you go final minus initial, you subtract the initial from the final. And so what we've done, go ahead, yeah.
I started the lab yesterday and I made the mistake of doing initial minus final instead. Can I write down and talk about my mistake and then multiply by -1 at the end?
Sure, that's fine. And okay, you can just do one sentence for the whole thing and that's all, you'll be fine.
Okay.
Okay. So this negative number means that when the electron went from the second orbit down to the first, it released energy. And that should make sense. If the electron is getting closer to the nucleus, then that means it's getting to a lower energy state, it releases its excess energy. If you think about it the opposite way, if you go from the first orbit to the second orbit, how would you do that? How do I make you jump off the ground? I hit you with a pitchfork in the behind, right? And that gives you energy to make you jump up. So if you want to go to from the first to the second, that would absorb energy. So that change would be a positive number. But anytime you drop from a high Bohr orbit to a low Bohr orbit, you're becoming more stable, you release energy. That's why this number is negative, okay? Now, how is that energy released? When an electron drops from one Bohr orbit to a lower Bohr orbit, the energy is released in what form? Who knows?
Photons.
It's released as a photon of electromagnetic radiation, exactly right. And the energy of that photon that's released is winding up going to be the exact same number you just calculated, except you take the absolute value of it, because when we talk about energies of photons, we don't give them negative values, we always make them positive values. So the energy released is given off as a photon, as is just said, and the photon's energy is always just going to be the absolute value of delta E. So you calculated delta E, it was whatever that number was, negative 1.634 times 10 to the minus 18th joules. So if you take the absolute value of that, you now know the energy of the photon that's given off. So that comes out positive 1.634 times 10 to the minus 18. Okay, so that's how you deal with changes in energy. Now, just as an advance, we'll talk about this in a couple of minutes, but now once that you've calculated how much energy the photon has that's released, what else can you figure out about that photon?
The frequency and wavelength.
So you can figure out the frequency because E, the energy of the photon, equals h nu, where nu is the frequency. So energy equals Planck's constant times frequency. You can solve for the frequency. And then once you know the frequency of that electromagnetic radiation, you can find the wavelength because speed of light equals frequency times wavelength. So good understanding, and that's what you're going to be doing in the lab today. Now, one other thing I'm going to ask you to do in the post-lab question today is calculate the energy needed to ionize an atom. So what does that mean? If an electron is actually removed from an atom, so it doesn't just go from a low orbit to a high orbit, it goes from an orbit pulled out completely out of the atom, we say that atom has been ionized. And it's going to take a certain amount of energy to actually do that. And so we're going to see if we can do an example where we calculate the energy needed to ionize a particular atom. So here's the example we'll do. We're going to calculate the ionization energy of a ground state hydrogen atom. Now, when we say ground state, and we saw this in our homework yesterday, you'll see it again this afternoon. Ground state means the electron or electrons are in their lowest possible energy states. They're as close to the nucleus as they can be. So for a hydrogen atom with only one electron, the ground state would have the electron in the first Bohr orbit, or according to Schrodinger, the 1s orbit. So what we're doing here is we're starting with the electron in the first Bohr orbit, and then we're ionizing it so it's going out of the atom. So just like the last problem, we have to calculate the energy where it starts and the energy where it ends up, and then we're just going to subtract those. So here's the energy where it starts. A ground state hydrogen atom is in the first Bohr orbit, so its energy will be negative K over 1 squared. And you can do that in your head, right? That comes out negative 2.178 times 10 to the minus 18th joules. That's where the electron is starting. We're now moving the electron. When it's ionized, where does it go? Out of the atom. So we need to figure out the energy of the electron out of the atom, and this is the conceptual one. I'll give you a conceptual way to think about this, and then a mathematical way to think about this if you're more mathematical, okay? Now, when the electron is in the atom, and there's a number right there, what do you notice about that number? What's true about the energy of an electron when it's in an atom?
It's negative.
Perfect, because that means attraction. If I took the electron and I put it next to another electron, what do you think its energy would be?
Positive?
Yes, because then it would be undergoing repulsion, okay? What if I took the electron, I took it out of the atom, and I put it somewhere in orbit around the Earth, thousands of miles away? What do you think it's, say it again?
It has no energy?
There you go, because it's not near the nucleus anymore, so it doesn't have a negative energy. It's not near an electron, it doesn't have a positive energy. So if it doesn't have a positive or negative energy, that doesn't give you very many options, it's got to be zero. So conceptually, when you pull an electron out of an atom, in the atom it has some negative attractive energy. When you pull it out, because it's no longer attracting to anything, its energy will be zero. Now, if you want a mathematical explanation for this instead, watch this, maybe you'll like this. The electron is right now in the first Bohr orbit. If we add energy to it, it's going to jump up to higher and higher Bohr orbits and maybe even eventually leave the atom. We can actually define as the electron leaving the atom as moving it to the highest possible Bohr orbit there is, which would be the infinitieth Bohr orbit. So if you move the electron to the infinitieth Bohr orbit, the energy of it would be negative 2.178 times 10 to the minus 18 joules over infinity squared. What does that equal?
0.
There you go. So there's a mathematical way to figure that out as well, okay? So now that you know where the electron's starting and where it's ending up, you know the energies. Our change in energy will be final minus initial. So your change in energy is going to be the energy of the electron out of the atom minus the energy of the electron where it started. So that's going to be 0 minus a negative 2.178 times 10 to the minus 18 joules. And that can be done simply. That just gives you a value of positive 2.178 times 10 to the minus 18th joules. This number came out positive. So when an energy change is positive, that means energy had to be absorbed. And that should make sense. If you have an electron attracting the nucleus in a hydrogen atom and you want to pull it out of the atom, it's going to require energy to do that, okay? So the positive energy change means that the hydrogen atom absorbed this energy in order to release the electron. So those are the concepts, the types of things I would like you to be able to do with the Bohr equation, where he's able to calculate the energy of an electron in the hydrogen atom. Now let's relate it to today's experiment. In lab, Dr.
I
White,
have a question. Sorry.
yeah,
So when the regarding the positive and negative energy, so when it is, if it's negative, that means the energy is being released, correct?
you actually made an incorrect statement. So let me just slightly correct your nomenclature there. When you have an energy of an object like an electron,
Mm-hmm.
a positive value means repulsion, a negative value means attraction. So you said when we get an energy that's positive, that means absorbed. So no, you have to be careful how you say that. When you say energy, the energy is positive or negative means attraction or repulsion. This is what you should have said. When you have an energy change that's
Mm-hmm.
positive, that means energy is absorbed. An energy change that's negative, that means energy is released.
Okay, got it.
Does
Thank
that
you.
make sense?
Yes, thank
I'm
you.
glad you actually said that. That's a subtle point. So Professor White in the lab today was determining the wavelengths of the hydrogen's emission spectral lines. And this is the data table that you're filling out. And there's two parts to the data table. She did a whole bunch of data and she had the numbers there. You had to record it for part one. That's where you're going to experimentally determine what the wavelengths of the red, the blue, green, and the violet lights are in the hydrogen emission spectrum. But the second part has nothing to do with that experimental data. The second part's going to be theoretical. And if you look at the columns under red, blue, green, and violet, in part 2, the column headings are 3 to 2, 4 to 2, and 5 to 2, because those are the transitions between Bohr orbits that produce the red light, the blue, green, and the violet light. So what you're going to do when you get to part 2 today, and this is the part where you probably had to listen to what I said for the last 15 minutes or so, you're not going to use any theoretical data in this part, okay? Anything from part 1, don't even use it. You're going to calculate everything in this part of the experiment only from the Bohr equation. And let's take the very first thing it says in part 2. It says energy change. So how are we going to calculate the energy change? Well, you're going to calculate the energy of the electron in the third Bohr orbit, energy of the electron in the second Bohr orbit, and then you're going to subtract them. And when you go final minus initial, that'll give you the energy change. Does that make sense? So that's going to be using the Bohr equation, and you'll actually use it twice for n equals 3 and n equals 2, then subtract. How do you get the photon energy then, once you've calculated the energy change?
You absolute value your answer.
The absolute value your answer, exactly correct. And so now that we have the photon energy, as was pointed out earlier, if you know the energy of the photons, you can calculate the frequency of those photons by going E equals h nu. We've just calculated the energy of the photon. We know Planck's constant. You can get the frequency. And then once you have the frequency, you can calculate the wavelength, because the speed of light equals frequency times wavelength. So everything here in part 2 has nothing to do with any data from part 1. If you're using part 1 data to do part 2, you're doing it incorrectly. Okay, so just so I point that out. Now for part 1, here you're going to use only the experimental data given, no Bohr equation. All right, so you're going to record all the data. So in the data table, you have a D value, an L value, a left reading value, a right reading value, and then boom, just from that, you should be able to calculate what the wavelength is for the red light, wavelength from the blue-green light, wavelength for the violet light. But I will not use my Bohr equation or my 2 electromagnetic radiation equations to do that. We have a different way to do that, and that was explained a bit in the introduction. I'm going to go through that again with you now so you understand how that's working. So when you are looking at a red light source, and the hydrogen is emitting red light, blue, green light, and violet light, so let's just talk about the red light right now. The reason you see red light is that you have all these red light wavelengths bombarding upon you, and here's what's important right here. The red light wavelengths are in phase. That means the crests are lined up, the troughs are lined up. And when you have waves that are lined up in phase, that increases the amplitude, the color becomes more intense, and you can see it. Now, when a whole bunch of waves approach either a prism or a diffraction grating, what they do is they actually bend through the diffraction grating. And they can bend at any angle they want, 1 degree, 2 degrees, 3 degrees, 4 degrees, 57 degrees, 82 degrees. Watch what happens. When they bend through it, let's say this particular angle here, as they bend, look what happens to the waves now. All of a sudden, the crest is now lined up with a trough. The waves have become out of phase. That means their intensity, their phase, their waves and crests, their crests and troughs cancel each other out. Their amplitude diminishes. You can't see the color at that particular angle. Almost every angle that the red light goes through the diffraction grating, this phenomenon will occur where the waves will be out of phase, so they cancel out their amplitude, so you can't see them. But there's only one angle that allows the red light to pass through the diffraction grating that keeps the waves in phase. That's this angle, not quite as big, a little bit less of an angle. If it does, now the waves are in phase, and you can actually see the red light emanating at that one particular angle. Now, the angle that it comes out at is dependent upon the wavelength of the light. Red has a certain wavelength, it's going to bend at this angle. Orange will not bend at this angle. Orange will bend at a slightly different angle. Yellow at a different angle. Green at a different angle. Blue at a different angle. Violet at a different angle. So that's why when you look at white light through either a prism or diffraction grating, like they did in the video at the beginning, the white light gets broken up into the entire spectrum. The reason you see red, yellow, green, blue, indigo, violet is because each wavelength gets diffracted at a slightly different angle to go through the diffraction grating so that its waves remain in phase. Now, what determines that? I'm going to focus in right there on the diffraction grating. Here's the two waves of red light coming into the diffraction grating. They bend at that perfect opportune angle. Well, if you draw a little right triangle here, okay, then this length of the side of this triangle has to exactly equal one red wavelength so that it exactly catches up with the red wavelength above. So when you form a triangle in which this leg, which I'm going to call E, exactly equals one wavelength of the light, that's when they're going to be in phase. So because orange light, yellow light, green light all have different wavelengths, this side will be slightly smaller, and that'll change the angle, and that means those lights will bend through at slightly different angles. So in this right triangle, that leg E is going to be the wavelength of the particular light that's impinging upon the diffraction grating. How is E related to the angle that it's bent through? Well, E and D, that's the leg and a hypotenuse, they're related to that angle through the trigonometric function sine. The sine of angle theta is going to equal opposite over hypotenuse. And so that's going to be E over D. So trigonometrically speaking, the angle that the light gets bent through is E over D. And if we want to solve for E, because that's the wavelength, I'm going to bring D to the other side of the equation. And so our wavelength of light, in this case the red light, is going to equal D multiplied by the sine of theta. Now, what is that D value? For a diffraction grating, that D value is the distance between the lines on the diffraction grating. And if you go back to the lab, I think it was like page 33 or 34 or something, they told you that the diffraction gratings we bought had 13,800 lines per inch. And they did a little calculation, where they did some dimensional analysis, and they figured out how far apart those lines were. So that numerical value is going to be D in this equation, the distance between the lines. I think it came out 1.84 times 10 to the third nanometers. So we actually know D. So if we know what D is, all you have to do is figure out the angle theta. And that's why the experiment we did was set up with meter sticks at right angles, because we were going to try to figure out what that angle is. And let me show you how that works. So you might recognize this setup as how Dr. White had the meter sticks forming a T pointing directly at the spectral tube, and you can see the diffraction grating in the front. So when you stick your eye right up next to the diffraction grating and you look at the spectral tube, you actually see the diffracted lines of red, blue, green, and violet on both the left and the right side of the spectral tube. So what we're going to form here is a right triangle. Watch this. From this diffraction grating, there's a leg of the right triangle here, a leg that goes over to whatever wavelength we're looking at, and then the hypotenuse comes back to here. So let me look at that from above. So here is the diffraction grating. We're looking at the spectral tube right there. Here's this distance here, and then here's the hypotenuse. That angle right there is the exact same angle we had on a microscopic picture before. So in this big triangle, if we can calculate theta, that'll be the theta we can use to calculate the wavelength. So what do you need to measure here? You need to measure L, and you need to measure X. So what is L? L is how far the diffraction grating is on that meter stick away from the spectral tube, and Dr. White showed you that number, or she showed you where it was sitting, so you can record that in your data table. Now, as long as you don't move the diffraction grating throughout the experiment, then that means L will always be the same number. So when you're analyzing the red wavelength, the green one, and the purple one, L will always be the same. The X value is what's going to be different, because X would be different if you're going to the blue, the green one, or the purple one, or the red one. The way we're going to figure out X is sort of a two-step process. We're going to first measure where the green wavelength is on the meter stick on the left side. So there'll be some number written there, and she showed that. Then you measure where the green wavelength is on the meter stick on the right side, and she showed that. You can write that down too. Let me make up some numbers. Let's say this green one was at 20 centimeters, and this green one was at 80 centimeters. So they called the distance between these two X. So if this one's at 20 and this one's at 80, what's the value for 2X?
60.
60. There you go. So if the distance between the two green wavelengths is 60, then the little leg of the triangle, which is exactly half of that, or x, would be 30. So you'll be able to, by subtraction and then dividing by 2, calculate what x is in each of these, and then you'll know the x value and the L value. If you know the x and L values, they will allow you to get the angle that the light is being diffracted through, because that angle is related to the two legs of a right triangle through the trigonometric function tangent. Tangent is opposite over adjacent. So that's going to be the x distance divided by the L distance. Now, what are x and L measured in? What units were on the meter stick that she was using?
Centimeter.
Okay, so what happens when you take 60 centimeters and divide it by 40 centimeters? What units do you get?
Millimeters.
Try again. Centimeters divided by centimeters doesn't equal millimeters.
Centimeters.
Centimeters.
Try again.
No
Centimeters
units.
divided by
No
centimeters
units.
doesn't equal centimeters.
They just cancel.
Mr. Martinez, exactly correct. They cancel out. There's no units. Okay, right? Because you have a centimeters on the top and a centimeters on the bottom, and you divide them out just like when you do dimensional analysis. So when you're getting the tangent of this angle, whatever the units of x and L are, they're going to cancel out. If you'd rather measure them in miles instead of centimeters, you're going to get the exact same answer as everybody else, because it doesn't matter what the units are. It's a ratio that has no units to it. Okay? So if we want to calculate what the angle is, I have to solve for it by taking the arctangent of both sides of these equation. So the arctangent of the left side just becomes the angle, and then we have to take the arctangent of whatever x over L is. It's a number that has no units. So you have on your calculator the little tangent button and the arctangent right above it. So second function tangent will allow you to do that. So this is how we get the angle. Now, we're trying to figure out what the wavelength was for the red light. So remember, we had this equation d multiplied by sine of theta. So I'm going to replace sine of theta with arctangent of x over L. And this is how you're going to calculate the wavelength of the red light and the wavelength of the blue-green light and the wavelength of the violet light experimentally. So you're not going to use the Bohr equation or any electromagnetic radiation equations. You will have calculated it experimentally by measuring L and x, and then going x divided by L to get a number, take the arctangent of that, take the sine of that, and then multiply it by d, which you remember is the distance between the lines on that little diffraction grating, which they calculated in the pre-lab as 1.84 times 10 to the third nanometers. That's how that works. Okay, that makes sense?
Professor,
Yeah.
so using D gives that 3 sig figs in, right?
Yes, because d is a
Okay.
3 significant figure number. That's correct.
Okay.
Now, let me point out one more thing that's going to happen to some of you today, and I'm going to see if I can save you from losing a point on the lab. Okay, so if you don't care about it, you can turn this off now, but if you want to see this, then stay with me for a second.
Question.
Question?
Yeah,
Yeah.
for that last equation, so that equation is the one we're gonna use to find the wavelength, the d sine, the last equation.
Yeah, that's what you'll use to calculate the wavelength of the red light, blue-green light, and violet light in part 1, the experimental part of the lab.
Okay, thank you.
Good. Now, at some point in your calculations today, you're going to be multiplying and dividing, and you're going to get a really, really small number for a couple of your answers. And some people's calculators will show a really small answer like this, because they actually can show it has enough places for you to put a digit in there, 0.0000000006. Okay. Now, if you divided a 3 significant figure number by a 3 significant figure number to get this answer, what answer do you write down in your data table?
3 significant figure answer.
So let's see, 0.00000006. And then what did I write down after that?
2 more zeros.
0, 0.
That's where I'm going to get you. Okay. Because this didn't didn't show the next 2 places after the 6, not because it was an exact number. It's because your calculator ran out of room to show you the remaining digits. If you contrast that to a number we had earlier today, where we did a division, we got 2.42 times 10 to the minus 18th, and it was supposed to be a 4 significant figure number. Well, it came out exact, so your calculator just put 2.42. But there was lots of room for the calculator to write extra digits if they weren't zeros. Contrast that to this. The 6 is way at the very end on the right side of the calculator screen. There's no more room for it to put another digit, so it can't put them. So if this happens to you, you don't want to write as an answer 0.00000000600 because you're making up those two digits. So what you do is you go to this button on your calculator that says SCI. That converts the number displayed on your screen from positional notation to scientific notation. So if you express it in scientific notation, bink, oh my goodness, now I can see what numbers would have gone after the 6 if it would have had room. It's a 6 and a 2 and a 3. So the answer then would be 6.23 times 10 to the minus 9th, or you could write 0.00000000623. Okay,